In this lesson, we're going to learn about one-way ANOVA and how we use one-way ANOVA to determine if multiple means are the same or if there's a difference in at least one of those population means. So one-way ANOVA uses the F distribution, and when we look at our data structure, you can see over here on the right that with the data structure, we have a categorical grouping variable, and we have 3 or more levels to that categorical grouping variable, and then we also have a quantitative variable. And quite often what we'll do is we'll take this data and the way that it's arranged in this 2-column table format, and we'll transform it to a different format where we have the groups listed as the titles of each column. And for hand calculations, it makes sense to do it that way. In some graphing calculators and other places, we'll have to have the data organized like that. But when we're using computer software, generally it'll be organized the way that we have on the left. So our hypothesis statements for one-way ANOVA will be always, our null hypothesis is the population means are all equal to each other, and we would have 3 or more population means. And then the alternative is at least one population mean is different from the other population means. Now, one of the challenges is if we reject H sub 0, all we know is one of the means are different. We don't know which mean is different from the other means or if they're all different from each other. We just know that at least one of them is different. So the example that I have that we're going to work through to kind of see this play out is a manufacturing example. It says, we are a manufacturer of marker caps that produced by 3 different machines, A, B, and C. All 3 machines are supposed to produce marker caps with the same inside diameter measured in millimeters. And then the table below summarizes the random sample of marker caps inside diameter from the 3 machines. Use a 0.05 level of significance to determine if there is a difference in the marker caps inside diameter produced by the 3 machines. Now, yeah, with this data set, it's way too small probably to be doing ANOVA with, but we're just doing this for example purposes so you can see the mechanics and the process of doing one-way ANOVA. And you'll notice at the top, I have these labeled treatments, factors, or groups because sometimes those terms are synonymous with each other. I'm not going to differentiate between those two, but just be aware of that when you look at output from various statistical software, calculators, or other places. They might use those terms to describe those. So the first thing that we have to do is we have to formulate our problem, and so we want to state the populations under study and the samples under study. So the population would be all marker caps produced by machines A, B, and C. The sample are the random selection of marker caps produced by each of those machines respectively. The variable that we're interested in is a quantitative variable. It's the measure of the inside diameter of the marker caps. And then we definitely need to identify the different population means. So mu1 is going to be the average inside diameter of all marker caps produced by machine A. Mu2 is the average inside diameter of all marker caps produced by machine B. And mu3 is going to be the average inside diameter of all marker caps produced by machine C. Once we formulate the problem, our next step is to write the null and the alternative hypothesis. H sub 0 is pretty easy. We only have 3 groups, so we're going to use mu1, mu2, and mu3 to represent those groups. And H sub 0 says that all 3 means are equal to each other. The alternative is at least one of those means is different from the other population means. If we reject H sub 0, again, we don't know which one is different. We just know at least one of those is different. Now, the other thing that I want to point out is we're using the F distribution for this, which the F distribution is the ratio of 2 variances. It's a right skew distribution. Since we're talking about the ratio of 2 variances, we can only have positive values, so this F distribution starts at 0 and goes towards positive infinity. And the nice thing with this is we're always going to be doing a right tail test. So this right tail right here is going to be our reject H sub 0, our null hypothesis region. And then the area to the left of that is going to be the fail to reject H sub 0 region. We have some conditions that we have to satisfy to verify that we can actually use the F distribution. So those conditions are as follows. The data is roughly symmetric or slightly skewed. Condition 2 is data has few outliers relative to the sample size. And so to check those 2 conditions, we'd be looking at the box plot and the histograms for all 3 of those groups, and we'd be checking all 3 groups when we go through and do that. We're not going to go through that here. And then condition 3 is the variation in the data within each group is roughly the same for all groups. And an easy way to look at this is to compare the interquartile range, the width of the box and the box plot, And as long as the largest width of the box plot is not 2 times or more larger than the smallest box plot, we're okay with condition 3. So you can compare the IQRs to make sure there's not a box plot that's more than 2 times the IQR of the largest one. After we check the conditions, we're ready to execute the calculations. And I have the outline of an ANOVA table right here, and we'll populate that with some of the information. So there's quite a few steps that we have to go through. Now notice in the blue, I have the treatments, the factors, and I have the term between groups. I'll kind of explain a little bit about that when we go through. SSTR is the sum of squares treatment. DF with the subscript TR is the degrees of freedom treatment. MSTR is the mean square treatment. And then we have the next row with the error, sum of squares error, degrees of freedom error, mean square error. And then at the very bottom, we have the total, sum of squares total, and degrees of freedom total. And then we have our F statistic and our p-value, which we'll get to last. So let's start off by taking a look at this, and we're going to go through and see how we calculate each of these sums of squares. If you're a student in my class, I'm not going to require you to calculate the sums of squares by hand, but we should know some of the relationships between the various values in this table. Technically, I could give you 2 of the sum of squares and 2 of the degrees of freedom, and you should be able to do everything else in this table, and you'll see when we get to the end of this. So the first thing I want to look at are the sum of squares total. This is the overall variability. And I know there's subscripts here that make it look a little bit confusing with the I's and the J's. Just think of the X with the 2 bars on this as the overall mean. So if we take all of these values and we add them up, they would add up to be 27. And we have 9 values in this table. So the X with the 2 bars over it, sometimes called X double bar or the grand mean, that's going to be 27 divided by 9, which gives us a mean of 3. And then X with the I and J, these are all the individual values right here that we see in the table. So all this is saying is take the individual values and subtract them from the overall mean, and then square those deviations, and then add up those square deviations. That's all this is saying. So for example, if I go through and do this, and I'll color code it with each column, I would have 2 minus that overall mean of 3 squared, plus 3 minus the overall mean of 3 squared, plus, and this is where I move to the orange, which I'll have to represent that with yellow, 5 minus the overall mean squared, plus 3 minus the overall mean squared, plus 3 minus the overall mean squared, plus 2 minus the overall mean squared. And then I move to the last column. I don't have a purple, so I'll use a blue. So I have 2 minus my overall mean of 3 squared, not cubed, squared, plus 2 minus 3 squared, and I'm going to have to cram this down below, plus 5 minus 3 squared. So when we go through and do this, 2 minus 3 is -1, squared is going to be 1, 3 minus 3 is 0, squared is going to be 0, 5 minus 3 squared is going to be 2 squared, which is 4, 3 minus 3 is 0, 3 minus 3 is another 0, 2 minus 3 is -1, squared is going to be a +1, and then 2 minus 3 is going to be -1, squared is going to be +1, the next one will be +1, 5 minus 3 is 2, and when we square that, that's going to be 4. So those are all the square deviations right there. And then the last thing I need to do is I need to take and add these up. So 1 plus 4 is 5, 6, 7, 8, plus 4 is going to be 12. So our sum of squares total is 12. That's our overall variability. And if we think about degrees of freedom total, we have a total sample size of 9. So it's really going to just be n minus 1, which is going to be 9 minus 1, which gives us a value of 8 for our overall degrees of freedom. So if I go back in the ANOVA table, we now know that the sum of squares total is 12 and the degrees of freedom total is 9. The next one that we're going to take a look at is the sum of squares error and the degrees of freedom error. So with the sum of squares error, sometimes this is called the variability within the groups. All right, so we're looking at the variability within each one of these groups. So there's a couple things that I need to know first before I do this. So the mean of column A, and I'm just going to call this X bar of A just to simplify this, that's going to be 2.5. The mean of column B, which I'll call X bar of B, this is going to be, if I add those up and divide by 4, that's going to be 3.25. And then the mean of column C, If I add those up, that's 9 divided by 3. So the mean of column C is going to be 3. And so now I can kind of come down and explain what's going on. So these J's right here, think of them as fixing the column. So all I'm doing is taking the mean of the column and then subtracting an individual value from that column from the mean, and then I'm squaring that value, and then I'll add those up for that column, and that'll give me the sum of squares for the column. And when I find the sum of squares for each of the column, I'm going to go out here and add all those sums of squares up. So again, to simplify this, I'm going to do this in the table so we see it. So we're going to have 2 minus 2.5, and we're going to square that. So that would be negative 0.5, and when we square negative 0.5, that's going to be a positive 0.25. 3 minus 2.5 squared. Again, that's going to be positive 0.25. I square that. That's going to be 0.25. And the way I'm going to write this is a little bit different, but I'm just going to say this is the sum of the x in column A minus x bar of column A. That's essentially what I did right there. I squared those values, and if I add those up, that comes out to be 0.5 if I add 0.25 and 0.25 together. So that's the sum of squares for column A. Now I move to column B. So I take 5 minus 3.25, and I'm going to square that. And when I do that, that comes out to 3.0625. And then this is going to be 3 minus 3.25. I'll square that. And that's going to come out to be 0.0625. And then again, we have another 3 minus 3.25, which again will be 0.0625. And then 2 minus 3.25 squared. And when we do that, that comes out to be 1.5625. So if I take and I add all these sums of squares up for column C, I'm just going to write that as the sum of column B, x of column B minus x bar of column B squared. If I add those up, those add up to be 4.75. So that's the sum of squares, the variability for column B measured by the sum of squares. And then the last thing that I need to do is I need to do this with column C. So we have 2 minus 3 squared, that's going to be 1. 2 minus 3 squared is also going to be 1. 5 minus 3 squared is going to be 4. So 1 plus 1 plus 4, this gives me the sum of squares for column C. X of column C minus x bar of column C squared, that gives me the value of 6. So now we have our sum of squares for each column. This outside summation sign over here on the left of the sum of squares error, we're simply going to take and add up 0.5 plus 4.75 plus 6. And if I add those values together, I get a sum of squares error equal to 11.25. Now I'm going to hold off on talking about the degrees of freedom error, and I'll do that at the very end, but the sum of squares error is 11.25. And here's a nice relationship between these, and I'll show this afterwards. But the sum of squares treatment plus the sum of squares error equal the sum of squares total. So we don't know what the sum of squares treatment is. So if you think about it, 12 minus 11.25 is 0.75. So the sum of squares treatment has to be 0.75. 0.75 plus 11.25 gives us 12. So that's one of the relationships in the table right there that we should be aware of. All right, so we're going to go ahead and we're going to jump to the sum of squares treatment. We'll talk about the sum of squares treatment and the degrees of freedom treatment. So with the sum of squares treatment, again, I know the notation looks a little bit confusing, but what we're doing is we're looking at the mean of the column, and then we're subtracting that from the overall mean, and then we're squaring that, and then multiplying it by the sample size of the column, and we're doing that for each individual column and adding them up. So I'll go through and I'll color code this according to the column. Just recall that our overall mean was equal to 3. We talked about that earlier about 2 slides ago. And now we just have to go through and do this. So first of all, for column A, our sample size is 2. We have 2 values in column A, times the mean of column A. If you remember x bar of column A, we said this was 2.5. So this is going to be 2.5 minus the overall mean of 3 squared. And then I move to column B. We have 4 values in column B. That's our sample size. If you recall, our mean of column B was 3.25. So down here, I'm going to have 3.25 minus my overall mean of 3 squared. And then my last column, I have a sample size of 3. My mean of column C was equal to 3, so this is going to be 3 minus my overall mean of 3 squared. 2.5 minus 3 is going to be 0.5, negative 0.5, and when I square negative 0.5, that's going to be positive 0.25, and when I double that, that's going to be 0.5. And then 3.25 minus 3 is going to be 0.25. When I square 0.25, that's going to be 0.0625, and when I multiply that by 4, that's going to be 0.25. And then in the last one, 3 minus 3 is going to be 0. When I square 0 and I multiply that by 3, that's still going to be 0. And then if I simply take and add these values up, I'll get my sum of squares treatment. So 0.5 plus 0.25 is going to be 0.75. And that's what we got when we use the relationship between those values on the table. Now, the next thing we want to do is we want to talk about degrees of freedom for the treatment. So sometimes these degrees of freedom, the sum of squares for the treatment, we call this the variability between groups. And the reason we call that the variability between groups is because we're taking the overall mean and comparing it to group A. We're taking the overall mean, comparing it to group B, the overall mean, comparing it to group C, relative to the respective sample size and adding those up. So it's the variability between groups is what we're looking at. So we're focusing in on these individual groups right here. Now, some books will use G for groups when we talk about this. I actually like to use K, but those are the same things. It's really the number of groups that we have in this data set. We have 3 of these groups. And when we talk about the degrees of freedom for the treatments, this is simply K minus 1. So in this case, we have 3 treatments. So this is going to be 3 minus 1. Our degrees of freedom for our treatments are equal to 2. So now if I go back to that ANOVA table, we've got some more information populated. We now know that these degrees of freedom are 2. And there's also another relationship here that we can see. The degrees of freedom treatment plus the degrees of freedom error equal the degrees of freedom total. So 2 plus our value of 6 is equal to 9. Now you can see right here our degrees of freedom error are the sample size minus the number of treatments that we have. So if I go back to that slide just to show this, we have K is equal to 3 treatments. Our overall sample size, N, is equal to 9 data points. So our degrees of freedom error is equal to 9 minus 3. Our degrees of freedom error are equal to 6. All right, so we've got the first part of this done. So like I said, all I have to do is give you any 2 sum of squares, any 2 degrees of freedom, and everything else in the table you should be able to calculate. Now the mean square treatment, this is really the sum of squares treatment divided by the degrees of freedom treatment. If you remember when we talked about the variance a while ago, when we calculate the mean square treatment, this is really the variance of the treatments. So I know it'll be kind of hard to fit this in here, but the mean square treatment, we'd have 0.75 divided by 2, so the mean square treatment is going to be 0.375. I'll write it down below right there. So that's our mean square treatment. And then our mean square error is the sum of squares error divided by the degrees of freedom error. So really this is the variance of the error. So 11.25 divided by 6 is going to give us the value of 1.875. And we generally don't compute the sum of squares total. So hopefully we made this connection right here. The way that I have my ANOVA table set up, if we take the sum of squares treatment divided by the degrees of freedom treatment, that gives us the mean square treatment. If I take the sum of squares error divided by the degrees of freedom error, this gives me my mean square error. So that's one of the other relationships in the table. Now the F statistic is the ratio of 2 variances, and it's the ratio of our mean square treatment divided by our mean square error. So in this case right here, our F statistic, which I'll write down below, is going to be our mean square treatment, which happened to be 0.375, divided by our mean square error, which is 1.875. And so this gives us a test statistic of 0.2. So that's our F test statistic. And this is always a right tail test, so the F test statistic is always going to be the lower bound. So I'm using the FCDF function to find my p-value. This is a function in your graphing calculator in a TI-84. So if I'm doing this, my FCDF function my lower bound is going to be 0.2. My upper bound is going to be 1 million. Technically, it's positive infinity. I just use 1 million, so you think it's a very large value. And then degrees of freedom treatment and degrees of freedom error. Sometimes it says degrees of freedom numerator and degrees of freedom denominator, just so you're aware of that. The numerator is always listed first. The denominator is listed next. In the numerator, you can see we have mean square treatment, and the degrees of freedom associated with that are 2. So we'll put that value right there. And then the mean square error is in the denominator of the test statistic. So the degrees of freedom associated with the mean square error are 6. And when we use this function on our calculator and plug those values in, we end up with a p-value of 0.8240. So that would be this value right here, 0.8240. And that's what we're going to use to make our decision regarding our null hypothesis in the next step. So just to recap, we have a p-value equal to 0.8240. We have an alpha value equal to 0.05. And now we have to use that information in the decision rule to decide what we're doing with our null hypothesis. So the rule is if our p-value is less than or equal to our alpha value, the level of significance, then we reject h sub 0. So our p-value very clearly is not less than our alpha value. So we'll make a statement. We'll say since the p-value equal to 0.8240 is not less than alpha equal to 0.05, we will fail to reject the null hypothesis h sub 0. So that means that there's not evidence to reject it. You could think of as it's really indicating that there's evidence that h sub 0 is true and h sub a is false. And if you remember in this hypothesis test, we wanted to know if there is a difference in the population means between these groups. That's what we're looking at, the difference in the marker caps. Inside diameter specifically. In the conclusion statement, we're going to say there is not sufficient statistical evidence to support that there is a difference in the inside diameter of the marker caps produced by machines A, B, and C on average in the population. So hopefully this helps you with navigating the hypothesis test on multiple means, 3 or more means, using analysis of variance.